Hello, today we're going through H9, which is our heat production and heat transfer experiment. This experiment consists of 3 different parts. Part A consists of using our Pasco software here in the lab to heat a heating element or a heating resistor up when in distilled water to record the change in temperature as time increases till it hits about 40 degrees. Part B consists of our heat transfer experiment. This experiment uses a spider dipped in wax to record the temperature traveling through our metal rods attached to the spider, recording as the wax melts, the time taken to get our thermal conductivity of the material. Part C consists of Newton's law of cooling, where using the same equipment as we used in Part A, we record the temperature decreasing over a time of 10 minutes to verify this law's existence. With that in mind, let's get started with the experiment. So, on screen currently, we have the equipment used for Part A. We have our laptop with our Pasco software, as well as our Pasco interface, which has our 2 thermometers connected to it, one measuring the room temperature, the other measuring the temperature within inside our heating system. We also have the heating element attached to the Pasco interface as well, which is what we use to heat up our resistor when it's submerged in our water. We have the scale, which we use to measure the mass of the water and the mass of the calorimeter. We use distilled water for our water so that there's no impurities in the water. For our heating system, it consists of a calorimeter, which has 3 components to it: an inner cup, an outer cup, and a spacer. The spacer allows for our system to become insulated from the outside, or as insulated as we can get it. The inner cup we fill with water, specifically distilled water, up to about 50 milliliters of water or 50 grams, so that it completely covers our heating element. For our data collection and experimental phase, we first start off by pressing our record button on our Pasco software and then turning on our resistor to heat up the water. We do this by pressing the on button in our signal generator section of the Pasco software. We allow the heater to heat up the water to approximately 40 degrees Celsius. At this point, we turn off the signal generator, but we keep recording for an additional 10 minutes to get our Part C for our Newton's law of cooling. The equipment used for Part B consists of a tripod, a heating mat, a heating pad, a Bunsen burner connected to a gas mains by a rubber tubing, our wax melt pot, as well as matches to light our Bunsen burner, and our materials set on a spider. For Part B, we'll want to put wax on the ends of our material. To do so, we rest the material against the edge of the wax pot, dipping in until we can dip in no further, thus getting about 1 centimeter to 2 centimeters coverage of wax on each of the ends of the material, as shown in the photo.
Reading clockwise from the handle at the bottom is N for nickel, B for brass, A for aluminium, SS for stainless steel, and C for copper. We'll place the spider on the tripod like this. We'll need to apply the heat from underneath. When you have the blue flame, just adjust it so that it's the hot flame on the Bunsen burner. We'll put the spider on the tripod so that it's applied to the center of the spider. start the stopwatch at the same time, and we'll speed up the clock a little bit. This bit of video, you need to note the time at which the wax melts on each one, so you might need to go over this a couple of times because the drips are hard to see, and you'll find out the times at which each one of those wax drips occurs on each metal, and compare that with the thermal conductivity of that metal. And you won't necessarily need to do the last one because it's just the order of melting specifically, but record the times all the same. Let the system cool. So we've turned the heater off. We're going to let it cool for about 10 minutes. We're going to speed the video up. You can see from the bottom graph, power versus time, that the power has dropped to 0, even though the voltage in the left-hand side you can see is there's something, but it's close to 0 and no power being added from this time onwards after a bit after 12 minutes. You can see from the top graph, from temperature versus time, that the maximum temperature has been reached and the temperature is starting to drop gradually. It looks like it's linear, but in fact that is an exponential decay towards it's approaching room temperature, the surrounding temperature, about 23 degrees. So that's going to take a very long time. So we're only doing it for 10 minutes. So we actually need to do a different graph of a log of the temperature difference versus time, not that one. Before we do that, we'll just get a couple of useful bits of information. We want to know the starting temperature and the maximum temperature while we were heating it. So we're just going to use the tool on the graph to choose in the green box just up to and almost including the maximum temperature, close enough. And if we click the right button, we should get the numbers for that. There we go. So the maximum and minimum temperature of the water, that's also the temperature of the inner aluminium cup, maximum and minimum temperature. The bottom graph, the area under that graph, is the amount of electrical energy added. Now that is in watt minutes. We want it in joules, which is watt seconds. So you'll need to multiply that number in watt minutes by 60 to get that in joules. So that's the amount of energy added electrically. Now, if you get the temperature difference between the water and the surroundings, that's theta, then take the log of that temperature difference against time. Because it's an exponential graph originally, when you take the log of it, it should be linear. And the slope of that linear section of the graph, whilst it's cooling, will be our cooling constant. And you can see in the box there that m is the gradient with its uncertainty. Now we need that number to calculate how much energy is being lost because of cooling through this. The other numbers we need for our calculations are the mass of aluminium of the inner cup. So we'll just enter that. You note that number. That's in kilograms. We also need the mass of water, also in kilograms, and we'll need to enter the gradient that we just measured off this graph from these measurements. And we'll use equations 9 and 10 from your manual and these numbers to actually calculate the next graph, which is the amount of energy lost from the system, P cooling, against time. And that graph looks like this. So that's a calculated graph from those numbers we've just entered. And you can see the area under that curve is the amount of energy lost actually over the whole process. Now what we're really interested in is just the area up to the maximum temperature, which is after about 800 seconds, which is approximately triangular. We'll let you use a triangle. The area of a triangle is a half base by height. The base is about 800 seconds. The height is about 1.3 watts. So you can work out the area from the area of that triangle. That would be the amount of energy being lost whilst it's heating up to its maximum temperature. So we'll just go back and just remind ourselves of the graphs at the beginning. So the bottom graph is the amount of electrical energy added to the system when you convert it to watt seconds or joules. The top graph will tell you the maximum and minimum temperatures of the water and the aluminium. You can use Q equals mc delta T to work out the amount of energy absorbed by the aluminium and the water. So you can compare how much energy you added electrically with how much energy was absorbed by the water and the aluminium, and then see whether the amount of energy lost because of cooling while you were heating it accounts for the difference.
With our H9 experimentation done and the associated theory and data analysis, if you have any questions, contact your demonstrator for any additional support. With that in mind, I hope you found this video helpful and enjoyable, and I hope you have a lovely day, and I'll see you next time.